And welcome to Enrich's makeup session for Newton's Laws of Motion Science Club session for September 2010. We're sorry we weren't able to meet because of the rain day, but we did want everybody to be able to get in the Science Club session they were scheduled to have for this month. So we decided to go ahead and just record it, and we'll do it this way. We're not going to make a habit of it because it takes a little bit of time to get something like this going, but we thought this was the best solution so that we didn't lose any time. So we're going to jump right in. So today we're actually looking at Newton's laws of motion, who do come from, of course, Sir Isaac Newton. He put them together in his Philosophiae Naturalis Principia Mathematica, published in 1687, where he laid out three very, very simple laws that we're going to cover today that really provide the foundation for what we call classical physics. Classical physics is one of those terms that sounds really complex, and it's not. When we talk about classical physics, we're really just talking about the physics of things that we can typically see and interact with. So more or less the physics of everyday life. You know, throwing a baseball, driving a car, observing the moon and how it rotates around the earth. Things like that really are described more or less completely by classical physics. Now, as you get more advanced into physics, you're going to see how that's not totally true and how it has some interplay with some things. But for the vast overwhelming majority of things that we do, classical physics gets it perfectly. So that comes to kind of note there. It's really, really handy to know this stuff. It's why we spend so much time on it. When you guys get into college and you start going through some of these things, you will spend your easily the first 3 or 4 courses of physics, if you get that advanced into it, on just classical physics topics. It's just that handy. So let's jump into the laws right off. First law, things in motion tend to stay that way until something else acts on them. Really, really kind of a complex way of saying that once something starts moving, it wants to keep moving. The only reason it stops moving is because stuff gets in its way. When you look at astronauts in space and you see how they'll throw things at each other, you'll notice it just keeps going until somebody stops it. And it looks like it could go on forever. And the fact of the matter is, for all intents and purposes, if it was a perfect vacuum, it would go on forever until it ran into something. That's the great thing about the first law. We know that things want to keep moving once you start them moving. Now, lots of things in real life get in the way. Things like air resistance, things like gravity. The ground is a real big one that I'm constantly coming into contact with. All these things really get in the way. So let's take a look at how this works out in practical example. I've got a ball here, and if I throw this ball, over time, gravity is going to start trying to pull the ball down as it's moving along. That's why when you throw a fastball, it's going to hit the ground. It doesn't matter how hard you throw it, it's going to hit the ground because inevitably gravity is going to apply so much force on it, it's going to drag it down. So let's look at that ball. Now, I don't know about you, I throw balls really badly, so I inevitably hit something like a wall. And in this case, what happens is when that ball hits that wall, they meet and the wall pushes back on the ball. It gets in the way of that ball wanting to stay in motion. And this is a force that we're going to talk about a little bit later. It's going to be really important. So we mentioned gravity. And that's a really, really important topic that is just super, super useful. It's super useful because gravity has a couple of attributes that we just absolutely love. First off, important to realize is that when we talk about gravity, gravity is not just centered on Earth. Everything has gravity. You have gravity, I have gravity, my iPhone has gravity. The headset that I'm recording this into exerts gravity. It's just really, really small. And the math behind that isn't all that sophisticated in all reality at the classical level. We're not going to get into it here, but it's worth noting that everything exerts gravity. Gravity is measured, in fact, between any two objects. Now, when we talk about gravity on Earth, we're generally talking about a very specific gravity. We're talking about the acceleration due to gravity is what we call it. And on Earth, on average, that's about 9.8 meters per second square. We talked about acceleration before, and so that's one of the things that you really want to keep in mind. When we measure gravity, we're measuring it as a form of acceleration, because what gravity does is it creates an acceleration from one object to another. So gravity, 9.8 meters per second square. Memorize it, learn it. It'll come in handy throughout just about your entire life. It is just one of those things that you will pull out over and over and over again. So let's go back to the laws. Second law. Force is proportional to mass and acceleration. Really fancy way of saying that there's a simple equation we can use to measure force. That simple equation is just force is equal to the mass times the acceleration. Now, as with everything, there's a more complex form of this, but for what we're doing here, this is just fine. Force equals mass times acceleration. So in other words, the amount of force exerted is equal to how quickly an object is accelerating and how much it weighs. And if you think about that, that makes sense. You know, if you drop something off of a building, well, the heavier things seem to hit with more force. At the same time, if you get hit by a ball, you know, a really light object that's going really fast actually hurts quite a bit. That's because those acceleration or those mass numbers are higher, resulting in more force. Really simple formula, and it turns out to matter in a whole lot of different things. Now, when we talk about measuring force, we use a specific unit. Now, we talked last month how units are really important, especially in physics, and that most of the time when you get yourself into trouble on a physics problem, it's because you weren't paying attention to your units, especially during your undergraduate work when you're dealing with classical stuff. With force, we measure it in a unit called newtons. Shock, surprise, it's a tribute to Isaac Newton. A single newton is just the force required to move a 1 kilogram object at a rate of 1 meters per second squared. It's a really simple measurement, easy to keep in mind. Just remember, when we're talking about force, we measure it in newtons, and we're talking about the kilograms per meter second squared. Third law. Every force from one object to another is exposed to an equal but opposing force from the other object. Now, you've probably heard this said a couple different ways. You know, for every action there's an opposite and equal reaction. That's not actually technically right. It's really for every force exerted on one object, there's an opposite and equal force exerted on the other object. And the difference is subtle, but it is somewhat significant. For example, when you're sitting in your chair watching this video presentation, you're exerting force on the chair. And as it turns out, the chair is exerting force on you. Now, you didn't commit an action. You're not bouncing up and down on the seat. I mean, you may be, but that's not what we're talking about here. You're sitting. Let's assume you're sitting down nicely. You're exerting a force on that chair right now. And that force is because of gravity. Gravity is causing you to accelerate towards the earth, and that's creating a force. At the same time, that chair is resisting you. And so it's creating a force in the opposite direction that's stopping you from plummeting to the earth, or at least to the floor in this case. Really simple concept, but very important to essentially all of the laws of physics. It allows us to do all sorts of neat things in terms of some things we'll call force diagrams that allow us to better understand how things interact. And we'll talk a little bit more about that in the advanced section, so if you hang out for that, definitely something to pay attention to. So let's look at an example, because this is not always all that intuitive. It's one of the things that I thought was really neat when I was researching this, is that this is not an obvious thing. So let's look at our guy here. We got a guy here, he's got a truck in front of him, and he's got his roller skates on, and he's doing something really silly. He's going to push on that truck as hard as he can. What's going to happen when he does that? He's going to roll backwards. The truck's not going to move. He's going to move backwards, even though he's putting force on the truck. Well, why is that? Well, think about it. Because of the third law, he is exerting force on the truck, so the truck exerts force back on him. Now, the truck weighs a lot more than our guy, and that's as evidenced by our circle here being really big. So that, let's say that's the mass of the truck, and the guy over there, that small ball, that's the mass of him. So much smaller mass versus much larger mass. And so when he pushes off on it, it doesn't move. He's not exerting enough force to make it move because of its mass. On the other hand, the truck is exerting force back on him, and it exerts more than enough force because of the difference in masses to move him, especially when you've got the roller skates on. So third law, really, really important. It really drives this home that anytime you have something creating a force on one thing, that thing creates a force in the opposite direction right back. What we're going to do today for your group experiments is we're going to just take some things and we're going to drop them. And then we're going to figure out how much force they exerted as they plummeted to the ground. It was going to be a lot of fun and really entertaining to do. But since we can't do that, we'll do the experiment all together. So I've got a little ball here, and it weighs 100 kilograms. 100 kilograms, about 220 pounds roughly. The question is, when we drop that ball to the ground, how much force is it going to hit the ground with? Well, we know how much it weighs, right? So we have the mass. Mass is 100 kilograms. Easy. What's the acceleration? It's gravity. Remember, we're dropping the ball. So the only acceleration we have is gravity pulling it down. We'll call it the gravity force, which is what we call it sometimes. But it's really the force due to gravity pulling it down. So we've got that. So we've got our mass. We know what our acceleration is. Our acceleration is gravity. And what's the acceleration due to gravity? What's the number for that? It's 9.8 meters per second square. So we've got mass of 100 kilograms, acceleration of 9.8 meters per second square. That gives us a total of just multiplying the two together. 100 times 9.8, it gives us a 980 newtons. Simple formula, really easy to calculate, and it tells you so much. Once you've got force, pretty much you've got access to everything you need in physics. You've already talked about acceleration, we've talked about velocity, we've talked about mass last month, we brought in force this month. Pretty much from here, most of classical physics is very, very accessible from here on out.